So, chapter 12 is about that could just get out of the way. So it's about polynomials and correlation, which are like two things that don't necessarily really have any reason to be crammed together, but that's what we're doing in this chapter. So like, hey, whatever. So just as a definition to recall, when we talk about a polynomial function, we're talking about something in the form a sub n plus x to the n, a sub n minus 1, x to the n minus 1, yada, 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 all the way down to a sub 1 x to the first plus a sub 0, where n is an integer that's greater than 0, and a sub n is non-zero. So this is just like some really technical, precise notation for describing what we inherently know to be a polynomial, right? Polynomial has a coefficient, a variable, and the exponent on the variable is a non-negative whole number, right? That's all we're saying. So just to kind of check, we'll just I'm going to write down some functions and we'll decide if it's polynomial or not. Sound good?
Yeah.
All right. So is this guy polynomial?
I don't know.
4x to the 6 minus 5x squared plus 2x minus 1.
Kind of looks like it. Yes.
Yeah, absolutely.
I like that.
So if we look, all the exponents are whole numbered and non-negative. There's nothing other going on other than addition, multiplication of variables and constants. That should be a polynomial. What's the leading coefficient in this polynomial? 4 is correct. What's the degree for this polynomial?
5.
The degree is?
It's x. It's x. 6.
It's 6. It is the exponent on the, or the largest variable exponent.
That makes sense.
Right? LC is leading coefficient. That's okay. How about the square root of 3x minus 6? Is that a polynomial?
Yeah. No. Go away with it.
Yes,
Absolutely.
it is. Why does the square root not matter here?
Because it's still a number.
Because the square root of 3 is just over the 3. The square root doesn't extend over the x. The square root of 3 is just a number. That's a fine thing. Your leading coefficient can be any real number, is fine. In this case, the leading coefficient is the square root of 3. What's the degree in this case? 1 is correct. Remember that there's always an exponent of 1 on that variable, even if we didn't write it. Oops. What if we have in this instead yes. The square root of 9x to the 4th plus 16x squared. No.
No.
No way, Jose. What's the matter with it?
The root's over the x.
Yeah, you got a root over the x.
Yeah, you can't.
How about this one? No, what's wrong with this one? Yeah, you got a negative in the exponent. Everybody cool with that? Okay. So let's talk a little bit about names. Yeah, don't fight, man. So, just a couple special polynomials. So there's the zero function. That is just f of x equals 0. The degree on the zero function is undefined, yeah. So the constant function is next. That's something where the form is just f of x equals a. And we should probably indicate that the a there is non-zero, because we don't want the constant function to be separate from the zero function. What's the degree there for a constant function? It's not 1. It is 0. Why is it 0? Because I can think about this as like a times 1, right? And 1 I can think of as x to the 0, right? So that's why the degree is 0. Everybody cool there? All right. We have linear functions. Which look like ax plus b. Again, a is non-zero, because if a was 0, we just have a constant function. We don't want to include the constant functions there. What's the degree for a linear function? 1. And we have quadratic functions. So those look like ax squared plus bx plus c, again, where a is not 0. What's the degree there? 2, right? So that's about all there is to it when we talk about polynomials here. Just going to be like, can you identify one of them and describe some parts of it? Like give it a name, whether it's constant or linear or quadratic, and give the degree and the leading coefficient or something. Like there's no actual mathematics going on, and just kind of applying some definitions and a little bit of vocabulary. That's the first section. What? So the next section is going to be about correlation. So correlation is just kind of describing how linear a set of points is. I guess would be a decent way of kind of describing that. So when we talk about correlation, we talk about whether it being positive or negative, and then whether it's like strong or weak correlation. So maybe we'll say positive versus negative, strong versus weak. Okay. So let's draw a couple of pictures here. So we're just going to kind of use our eyes here to do this. We're not going to, again, do any kind of computation. So here is an example of some strong correlation. Because if I look at this, it looks like these points resemble a line pretty closely, right?
Yeah.
If I were to try to draw a line of best fit through there, all the points are relatively close to that line of best fit. As opposed to this guy, which I would call weak correlation. Oops. If I were to try to draw a line of best fit through this, we got some stuff that's pretty far away from that line of best fit, right? The average distance is it's almost twice as much probably as the other situation, right? We'd say that correlation is a little bit weaker, or we'd say it's weaker. Notice that the line of best fit in our first example, that line would have a slope that is positive. So that correlation we'd call positive. And here, the line of best fit is going down. It has a negative slope. So here we'd say that this correlation is negative. Now we haven't done any calculation here so far, right?
Oh, yeah.
Now we would like a way to quantify this relationship, right? Rather, it'd be better to have a numerical measurement for this term correlation than just like look at it with your eyes and be like, is this one better than that one? Sometimes it's hard to tell that just by looking at it with your eyes. So the measurement that we use to do that is called the correlation coefficient. And we use the letter R to represent that value. And specifically, what this correlation coefficient is, it's the average distance of each point from that line of best fit. So some properties of the correlation coefficient. One of them is that the range of values that correlation coefficient can take on are the numbers -1 to +1. So if R is less than 0, that means that we also have negative correlation. Similarly, if R is greater than 0, we have positive correlation. We'd say that if the absolute value of R is close to 1, we have strong correlation. And if R is close to 0, actually I probably don't need the absolute value there. I'm going to leave it anyways. That means we have weak correlation. Okay with that? Now I want to make a little bit of a point here that if you actually calculate correlation coefficients, you won't ever actually be able to get a correlation value of 0. It's like more of a theoretical value. That would indicate that the points are like literally random, which, like, from a finite perspective, you can't really get. So you won't actually ever see a correlation value of 0, but that's fine. Now, the value of 1 or -1, you will actually see that happen. So if all of the points in your data set actually lie on the line of best fit, that would give you an R value of either 1 or -1, depending on whether the slope of the line was positive or negative. So that's possible. But you wouldn't actually see a value of 0 coming in. Just to be clear about that. So let's do a little example where we find this value for R. So let's say that this is our data set. And say we wanted to find that value of R. We're going to do this entirely on our calculator. There's like a formula for how to do this by hand, but I'm not interested in coming up with that. I'm also at the same time going to draw a scatter plot of this data, generate the line of best fit, and graph the line of best fit all at the same time. Mr. Salick, what can I do you for? Yeah. Yeah, I don't blame you. They've been in my class all year, and I still sometimes don't know their names with their masks on. Or with their masks off, for that matter, because I never see their faces either way. Okay. So, I'm going to do this on my calculator. If you'd like to follow along on your calculator, that's cool. You don't have to, because again, we're recording this. It'll be in the videos on PowerSchool. You can always go back and watch it if you need to. So what I'm going to start by doing is inputting this data into my calculator. The mode won't matter. Well, I mean, you need to be in rectangle or function mode, but degree or radians doesn't matter. Okay. Since we're going to graph a line, you can't be in polar mode or something, you know. But that's a fair question. Anyways, to input data, we're going to go to the Stat button. From there, we're going to select the Edit tab and the Edit command. And I have a bunch of data in here already, apparently, so I'm going to clear some of this data out. Most of you probably don't have any data in there. If you want to delete an individual entry, you can go down and just press the delete button on it. But I have a whole list of values that I want to get rid of. So the easiest way to do that is to move up to the name, press clear, and then the down arrow, and it'll wipe the entire column for you. Don't press delete on the name, press clear, and then down. If you press delete, it gets rid of the name also, and then you have to go back and rename your list. It's a big hassle. Just try not to do it. It's fixable, but it's a hassle. So in my L1, I'm going to type in the prices here for the cans. And obviously, I'm not bothering with the zeros at the end of the decimal point. Is that cool with everybody? In the second column, I'm going to put the number sold. So I'm basically just copying this thing into my calculator right now. Everybody cool with that? So that's easy, right? What I'm going to do now is I'm going to graph these points just to give myself a visual of what it is that I'm going to be finding the correlation for and the line of best fit for. So I'm going to exit out of here by pressing second in mode. To graph points, what I'm going to do is press second and the y equals button. This opens the stat plots menu. From the stats plot menu, I'm going to pick one of the plots. It doesn't really matter, 1, 2, or 3. I'm just going to pick one. I'm going to start by turning it on. I want to plot just individual points, so the first option there on the type. When I type my points in, I type the x's into L1 and the y's into L2, so the default L1 and L2 are there. And I like using the squares for the points, so I'm going to go ahead and do that. Now, to graph this, I'm going to press the window. Oops. Okay, I'm going to exit out of here first, apparently. And then I'm going to press the window button. So my x values went from 2.5 to 1.5. So I'm just going to go from like 0 to 3 seems pretty good there. Or 0 to 4, whatever. Sound okay with you guys?
Yeah.
I'm going to go up by quarters since that was the increment that things went. So I'm going to make my tick mark by a quarter. My y values went from 80 to 207. So maybe I'll go just from like 0 to 300. Seems like that'll capture all my points with some room to spare. And I don't know, going up by 50 seems reasonable there. That gives me like 6 increments or whatever. And then I'm just going to hit graph. Oh, I got some gobbledygook in here. I forgot to turn off my plots. Get rid of that guy. So there's my data. Everybody cool with that? Okay. So that's just the scatter plot. If I were to approximate the R value there, would you say that's strong or weak? Pretty strong, right? If you're going to give it a numerical value, maybe somewhere between 0.8 and 0.9. Is that positive or negative correlation? Negative, because the slope is kind of heading down, right? Cool. All right, we're done with that. What I'm going to do now is I'm going to generate the correlation and the line of best fit in one shot. So the calculator can do both those things at the same time, which is lovely. To make sure that we get the correlation to pop up, I want to do one thing first, is I want to make sure that our calculator have the diagnostic turned on. So if we do this all at once and the diagnostics aren't on, it won't report to you the correlation. And anytime we want to make a line of best fit, we're going to want the correlation anyways, and it's easier to do that than try to get the correlation separately. So we're just going to do this all in one shot. And once you've turned the diagnostic on once, you shouldn't have to do it again. So let's just do it now, just in case. So the easiest place to get this is to just go to the catalog. So I'm going to press second and then the 0 button. And I'm going to go and find the command called diagnostic on. So I could scroll all the way through this. It's alphabetized. Or I can press alpha and then the button with the D on it to skip down to the letter D's. And then scroll till I find diagnostic on. Everybody see that? Did you find it?
Yeah.
Once you found it, press enter. It'll paste it onto the home screen. And press enter again. And when it says done, that means the diagnostic is now turned on. And it should stay on until you like reset your calculator or something. Everybody cool? Okay. Yes, sir.
Is it different for the color calculator?
Should not be. Should still be the same. Should still be the same, regardless of the version. I don't think any of these things changed with the operating system updates. So you should still be able to find that in the same place the same way. Is that cool? Did you find it? Okay. So what we're going to do now is we're going to create our line of best fit and get our correlation value all at the same time. So I'm going to press the stat button again. But this time I'm going to go over to the calc tab. And from the Calc tab, I'm going to select the linreg option. It doesn't matter which one. There's another one that's like b plus ax or something. Whatever. It doesn't matter. Pick the first one. So I think most of us, this puts us in a menu like this. Does anybody not get the menu? If you have a super old calculator, this just takes you to the home screen without the menu. Okay. If that ends up being your case and you didn't have your calculator here to realize that, just come see me and I'll show you what to do. So if we remember, we put our data, we put the x coordinates into L1, so the x list should be L1. We put the y coordinates into L2. Notice mine right now says L3, so I'm going to change that. Notice above the numbers 1, 2, 3, 4, 5, 6 in blue is L1, L2, L3, L4, L5, L6. So I'm going to press second and the number 2 to change that to L2. Most of you guys are probably defaulted already at L2, so you probably didn't have to do anything. Frequency list is something we're never going to use, so just ignore that. Nothing will ever go there for any of the problems we're going to do in this class. But store reg EQ, I do want to do that. So this is going to generate a line at best fit. I want to save that equation so that it'll like paste it into the y equals menu for me so I don't have to like recopy it. It'll save me some hassle, especially because the numbers are probably going to be kind of weird. So what I want to put here is the variable y1. So to get that variable, what I'm going to do is I'm going to press the vars button, which is right underneath the down arrow. I'm going to go over to the yvars command since I want a y variable. I'm graphing in function mode, so I'm going to pick the function command, and I'm just going to grab the first one, which is y1. Once I've done that, I'm going to scroll down to calculate and press enter. So what this is output for me is the type of equation I've made, which is a linear equation. It tells me the slope and the y-intercept. So if I were to write down the equation, I'd write y equals negative 104.68, yada, 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 times x plus 329.28, yada, yada, yada. Everybody's good with that? And then it tells me my correlation coefficient, my value for R is negative 0.96 and change. Don't worry about what the R squared is. We don't care right now. Yes, sir.
Sorry, what did you put in the store
Y1. Yep. So vars, yvars, function, and then Y1. Okay. So if I go and I press the y equals button, you'll notice that if you do that, in the y1 spot, the equation that it just displayed to us is already posted there. That's pretty cool, right? If I hit graph, there's my line of best fit already on my graph. That's pretty cool. And let's say, what if we wanted to find or predict the like the number of cans that we'd sell if we charged, I don't know, like 50 cents or something, right? Like that's something you might be able to do now with this line of best fit. Everybody agree? So one way I can do this is I can press second and the trace button. Select the value command. So at the bottom of my graph now it has x equals with a flashing blank cursor. I can type in a value for x here, so maybe 0.5, and press enter. So you'll see my cursor is now flashing here on my line of best fit, and it tells me the y coordinate to go along with that. I'd predict to sell 276 cans of soup or whatever these are. Pop. Yes, sir. Of course. Now the drawback to doing this problem the way that we just did it is that if you are looking for a value that's not on your screen, you get an error, right? So you could either change your window so that the point that you're looking for was on the screen, or we could do it this way also. So from the home screen, you could do vars, yvars, function, y1, and then just do y1 of 0.5, like function notation. And then it doesn't matter whether it's on the graph or not. It'll always report back a value for you. Everybody's okay with that? Okay. A little piece of vocab here. So if we want to predict a value like how many cans we'll sell if we charge 50 cents, where that point is outside of the range of values we built our model from. You guys see that? That if I were to plot that point that is outside of the points we used, we'd call that type of thing extrapolation. If we had picked a value that's in between two of these points, like say $1.90 or something, that's called interpolation. Which one of those do you think consistently gives a more reliable result? The interpolation is a much more accurate estimate, right? Imagine if you were like, trying to project, the height of some person based on their age, and you surveyed people and you just collected data from people between the ages as they aged from like 10 to 16. And then you're like, oh, how tall are you going to be when you're 36? Are you going to get a real good estimate out of that? No. Why? You stop growing eventually, right? You picked like the meatiest part of your growth curve. You know what I mean? Okay. Okay. So that is a linear model that we just talked about. So you're building a linear equation, a line of best fit. Now there's other types of models as well. So these other models are nonlinear. So we need a different way of kind of describing their correlation, because the correlation coefficient is talking about the average distance to the line of best fit. If our model is nonlinear, there's no line of best fit, right? So we're going to be using instead something called a coefficient of determination. That's the R² value that had appeared earlier. Now you can still calculate a coefficient of determination for a line, but you can also do it then for, a parabola or a ellipse or some other shaped curve. So again, with a coefficient of determination, basically all the same rules apply, except instead of being bounded between -1 and +1, you're bounded between 0 and 1. But the closer you are to 0, the worse fit it is, and the closer you are to 1, the better fit it is. There's no positive negative to it anymore because it's not a slope situation. So some other types of models. The first one we'll talk about is the power function. Just want to double check here. And when I say the first one, I meant the only one we'll talk about. Oops-a-daisy. So the power function is going to be written in the form of k times x to the a, where k and a are non-zero. K we refer to as the constant of variation, and A is the constant of proportion. So some examples of power models. Say like we're talking about the circumference of a circle. This is a equation in two variables, c and r. Here the k is 2 pi, and the a is 1. So we'd say like the circumference varies with the radius. What if we had the area of a circle is pi r squared? So here the k is pi and the a is 2. So here we'd say the area varies with the square of the radius. What's up? Yeah. Yeah. So again, the form is the a is the exponent on the variable, right? So what if we have volume equals 4/3 pi r cubed? It's the volume of a sphere, right? The k here is 4/3. The a is 3, and we'd say that the volume varies with the cube of the radius. Everybody's cool there? Yeah, Cass? Oh, thank you. Let's look at an example where we build our own power model from some data. So here we have the distance from the sun in gigamiles and the orbital period in number of days. So how long it takes or how many days it takes for it to pass around the sun. So we're going to start by, creating a model, like a scatter plot. Then we'll fit a power model to that scatter plot to find the coefficient of determination. And then we'll use that to estimate the orbital period for Neptune. That's not on our list. Sound good? So we'll start by entering this data into our calculator. So you press stat and then from the edit menu or tab, pick the edit command. I'm going to clear all my stuff out of there, or you can just type over it. It doesn't really matter. I like to just get rid of it because I'm a bonehead and make like stupid mistakes because I'm not paying attention and don't notice that something didn't type over in the right way. But, you know, whatever floats your boat, you find what works for you guys. What's your favorite planet in the solar system? Yeah? You like Venus. I'm a Jupiter guy. I like Jupiter because it has the best variety of moons. So, outside of Earth, the most water in the solar system is located on Europa, which is one of the moons of Jupiter. Well, it is quite cold. And the most volcanically active location in the universe is the moon of Jupiter called Io, which is pretty much like constant massive volcanic eruptions all the time. Yeah. And the location other than Earth, or the location on the solar system with an atmosphere closest to Earth, is the moon Titan. That's actually one of Saturn's moons. But it has a nitrogen-rich atmosphere similar to Earth's. I do, but they're not usually about space facts. This is just from being a geek. I mean, I have a very good memory. It's not, I don't know if it's photographic or whatever, but. What's up? Of course. Do I grade that fast? Oh, I don't know.
Some teachers take a long. You grade faster.
Okay. Well, the homework, it's worth so little, I don't spend a lot of time grading it, so I can grade it very fast. You know? All right, so we got this in here. Let's go ahead and plot this real quick. So my x's go from 57.9 to 1,047. So I'm going to go like 0 to, I'm going to go all the way to 5,000 because I know that Neptune that we're going to use has a, whose distance from the sun is 4,497. So I'm going to pick 5,000, so that's included in there. Just go by 500. Neptune's really far away, guys. Our y's, the orbital periods, go from 88 to 10,760. And then Neptune's, I'm guessing, is going to be a whole heck of a lot bigger than that. So I'm going to go from like 0 to 50,000. Again, if you didn't pick what I did there, it's probably fine. So I picked that, hit a graph. Yeah, and most of them are down here at the bottom. That's not surprising, right? All right, whatever. Exit out of there. Let's build our model. Stat. Calc. This time I want the power reg, which is there at option A if you keep scrolling all the way down. Yeah.
Why are we using that now?
Because these are not linearly related. If we looked at the data a little bit more, you'd see it was kind of curving.
Yeah.
Like that. So we're still using L1 and L2, and I'm going to store my regression equation again because I want to look at the graph. I'm going to store this one also into Y1. It'll just overwrite the other one that's in there, so there's no worries about that. And I'll hit calculate. So there is my power model. It tells me my value for A and my value for B. And there's my R squared value. Everybody cool with that? So if I hit my graph, there's my power model. Pretty cool. And I wanted the value or the orbital period for Neptune. So I'm going to do, or approximate that. So I'm going to do y1 of, and the distance from Neptune to the sun is 4,497. Whoa!
400 what?
4,497.
Where is that? I don't see it.
It's not on the table. I'm telling it to you right now.
Oh, it's 60,000.
Yeah, that's a lot of days.
More.
It takes a long time for it to get around, huh? What do you guys feel okay?
1 year for Neptune is 114 years.
Yeah,
If I did my
I trust you.
that, not one person will be alive with the rotation of Neptune.
No, you underestimate like how far things are apart.
Okay, I lost my thing.
What's even odder is if you look at the atomic scale. Like if you looked at how far like the nucleus is from like the electron shell, it's proportionally even farther apart than the planets are from the sun.
That's inside us.
And that's like, yeah, that's like your particles. Like mostly it's empty space.
Okay, great.
There are more trees on Earth than stars.
Look at it. Look at it.
I don't know if I believe it.
What's up?
No.
It says there are more trees on Earth than stars in the Milky Way.
Mm.
I don't know if I believe it.
Well, here's the problem: is how do you measure how many stars there are in the Milky Way? Because what you're seeing is light from like 1,000 years ago. It's not actually the star's current light. So who knows if they're still there?
It could be burned out.
How do you count them all? You gotta travel to each one.
But by the time you've traveled to one, maybe stuff is, like new stuff has popped up or has gone away.
It's just too much work.
Because you can't fly faster than the speed of light, Anthony. It's going to take...
Not yet.
Not yet. Watch me. You guys are awesome. All right. Anyways, that was it for chapter 12. We're done. Notice nothing in there was complicated, right? The worst stuff was like learning how to use your calculator competently.
Why do people keep doing this? They're like going into the circle, and I can't do how.
So I'm going to stop the recording.